Okay, so now our control is actually to achieve the vector control. Different people will adopt their own topology, but in our case, to make the system user friendly, we have taken rotor flux rotor as a reference, and we are making an analogy of the performance of an asynchronous induction machine equivalent to a separately excited DC machine. In case of separately excited DC machine, we are getting two galvanically isolated circuitry for torque and RPM control, field control. If you increase, if you change the armature current, your torque will be changed, whereas your field will be constant, which is entirely independent of speed of the machine. And simultaneously, if you want to change the flux of the machine, the field excitation you can change, but your torque will be unaltered. But this is possible because your torque producing flux and your back EMF producing flux both are quadrature in nature in case of separately excited DC machine, but whereas in asynchronous induction machine it is quietly different. That's why for an induction machine, a certain instant, if the machine is drawing say 10 ampere current, so we cannot, there is no straightforward correlation that we can predict. We can tell how much ampere is responsible for torque production and how much ampere is responsible for flux production. So we have to do some analysis, we have to do something so that we can make an analogy of the asynchronous induction machine equivalent to a separately excited DC machine. So in our case, we have aligned the rotor flux with the direct axis of synchronous rotating reference frame, and due to that reason your quadrature component of the flux rotor flux becomes 0, and the entire rotor flux is lying on the direct axis, and you are getting an analogy of the torque equation for an asynchronous induction machine equivalent to separately excited DC machine. So there are I am not going to the detailed calculations, but I will explain very simply the topology. So this is your machine, and these are the three phases. So this is the three phases. Here you tap the current. So these are say IA, IB and IC. So now here we are using one conversion. Here we are using a conversion which will that A, B, C, that's three current will take, and it will directly convert to DQ axis. But it is a rotating axis, definitely you need theta, and how this theta will come I will explain. So this is theta. Okay, so here you will get direct axis current and quadrature axis current. So definitely this direct axis is responsible for flux production, and this quadrature axis is responsible for torque production. Now these things, now what I will do, this is my field reference, this is my field reference, that is my input, one input, sorry. Just 1 minute. I'll put in airplane mode so that nobody can disturb. Okay, this is my field reference. So this is I am comparing, and this feedback I am taking from this ID. So this is my ID, and here there is a flux controller. This is a PID or PI, whatever may be, and from there I am generating the direct axis voltage. So this is one part. Another is my RPM. So this is my set, this is my reference RPM, this is my reference RPM. So this is my set RPM at which I want to rotate the machine. And again here there is this is the feedback. This feedback I will take from the I will take from a tachometer, or is a shaft incremental encoder. So this thing is coming here and it is compared. Again there is a PID, again there is a PID. This PID, after this will get the torque producing component reference, means IQ reference I will get. Then again this is to be compared with this IQ, and I will again there is a tuner here. The PID will be tuned properly and will generate the will generate VQ. So now here is one thing. Now once you get this VD and VQ, so this is my this is here, it is my VD and this is my VQ, and from there I have to get VA, VB and VC. This is my reference voltage for my switching, means here this is the DQ, here ABC axis. So here again I want theta. So now once I get this ABC, now this is to be compared, means this is a comparator. So here there will be 3 comparators. So this one and this one comparator, minus. So minus are connected with this is here, it will be my high frequency carrier and it will go here, this will go here and this will go here, and these are the my switching pulse. So one will go to A phase positive switch, and the inverted one of the same this is this one. So this will go to R phase positive switch, and this will go to R phase negative switch, and similarly this will go to Y phase positive, and inverted one, it will go to Y phase negative switch. Now how to estimate the theta? So to estimate the theta, what we have done, so to estimate the theta, basically we have, so we are generating, see here, this is my field reference, and this is my field reference, means this is my direct axis current reference, and that is my quadrature axis current reference. So if you divide both, that calculation I will tell you later. So this is a divider, so this is, here is coming my ID reference, means field reference, and here it is coming IQ reference, that is my torque reference. And now if you multiply with the inverse rotor time constant, what is TR, you will get omega slip. This is a simple mathematics that now I am not explaining. So omega slip, basically your omega slip is equal to synchronous speed minus actual speed of the rotor. Now if I add here, if I add omega r, basically omega SL is equal to omega s minus omega r. If I add the again actual speed, this omega r, this omega will cancel, and output will get omega s. Basically your omega s is equal to d theta by dt. So if my theta is equal to omega s integrate dt. So here if you put on integrator, you will get theta. This theta will be given to this block as well as this block. So my control is completed, and this is the overall control topology of the system. Based on these things, if you are giving some positive signal to me that it is possible, then we can discuss in detail all the things and the queries and how to go ahead. So please look into the matter and try to give me feedback by tomorrow evening. Thank you very much.